All right, welcome to the weekly M-Cubed seminar. Today our speaker is Kristian Strommen. Kristian is from Oxford University, not to be confused with the University of Mississippi in Oxford. It's Oxford, England, right? Yeah. Got his PhD in 2013 in pure math at Oxford. Then right after that, he took a postdoc with Tim Palmer, working on the impacts of stochastic parameterizations and resolution in climate models. In 2019, he was given the Thomas Phillips and Jocelyn Keene Jr. Research Fellow in Climate Science at Jesus College in Oxford, continuing his work on stochastic climate modeling. In the last few years, he's been shifting his focus towards questions around mid-latitude predictability and regime dynamics. And today his seminar is on jet regimes and the predictability of Euro-Atlantic. No. Oh, okay. There's somewhat changed from the, okay. North Atlantic Oscillation. You could all read this anyway. Right? They say that, over here we say that, the second hardest thing in getting into Harvard is getting out of Harvard. There must be a similar phenomenon there at Oxford.
That's true, yeah. Sticks your claws into you. So.
Okay.
Okay, hopefully this microphone is on. Okay, great. So thanks very much for that introduction, Richard. It's a pleasure to be here visiting NCAR. Thanks to my host here, Judith Berner. I'm going to talk about, not about stochastic climate modeling, but about mid-latitude predictability, and in particular, the North Atlantic Oscillation and how we can kind of understand some curious features around predictability of this using so-called jet latitude regimes. And the joke in the subtitle will hopefully become apparent before the talk is over. I'm going to flash some names on the screen. There's loads of people I've talked to who've given invaluable input on this stuff. Here's just a few of those names. Okay, so what's the motivation? The motivation is essentially, right, that the winter NAO, so the NAO, probably most of you are familiar with this, right? But it's this pressure pattern, a dipole of pressure visible here. And it's a good, like the mean state of this NAO pattern in winter, by winter I mean DJF, is a good first order approximation of winter weather in Europe, and at least to some extent on the east coast of America. So it's natural to wonder if that's predictable. Just before we get into questions of predictability, just to sort of get a better understanding of why this is a good first order approximation of at least European weather. So because I'm in England, the talks I've given about this have mostly been about European impacts, and so I'm not going to say anything about East Coast USA, but I'm sure something maybe similar occurs there. But for the UK and Europe, it's very kind of easy to think about what happens. So here's a great example, which I lived through in winter of 2020. We had this very strong positive NAO pattern, seen here in geopotential height anomalies. Why that affected the UK so badly is easier for me to understand just thinking about what the jet stream is doing. So this is zonal winds, and you see the jet in red. Essentially, this is what the jet looked like for most of that winter. And what that meant is that every single storm pretty much that developed over the Atlantic just got swept in and hit the UK. So we were really being hammered by a new storm every single weekend pretty much for a few months. And of course, you got loads of flooding and things like that. Besides just precipitation impacts, there's a lot of impacts where the jet stream has a big impact on temperature anomalies. Of course, the jet stream is somehow a very sharp boundary between the cold polar air and the warmer tropical air. So when the jet stream gets stuck in some kind of undulating pattern like this, you get these warm or cold air intrusions coming in, and they can persist for several weeks, and you get extreme cold weather or extreme warm weather, depending on where you are. So it's obvious to ask if we can predict this. And when I talk about predicting, I mean in a seasonal context. So I mean, can we initialize the forecast model on the 1st of November and try to get an idea of what the average winter conditions are going to look like? And for context, this video is showing just a sort of sample of what the winter Z500 anomalies look like for a particular year, and it's a swirling mess of chaos, right? It's sort of hard to imagine we might be able to predict somehow what is going on here on average, even on average. But it turns out we can. So models nowadays, at least some models, show really good skill at predicting the winter NAO from 1st of November. But they also show this interesting phenomenon, which has been called a signal-to-noise paradox. And what is that? Well, first of all, I should just say this is a feature across essentially any model which shows some skill at predicting this NAO. Winter NAO shows this paradox. And to understand what it is, it's useful to consider a kind of canonical example. This is the UK Met Office, a paper by Dunstan et al. They tried to see how well their model could predict the winter NAO. So what this plot is showing is a so-called hindcast. So in case you aren't familiar with that, what you do is you take your state-of-the-art forecast model, in this case the Met Office model, and you initialize it in the past. So you go to 1980, that was the first year in this case, you initialize your model with initial conditions November 1st, 1980, and then you try to let your model predict the winter of 1980. And then you do that for every year from 1980 to 2015 in this case. That gives you the red line, which is the ensemble mean. So each of these forecasts are actually an ensemble of forecasts, right? And then you take an ensemble mean as your prediction, your best prediction of that year. And that gives you this red line. And the black line is what the actual NAO, winter NAO, did according to reanalysis data. And the Met Office, the UK Met Office, kind of shocked the community to some extent by showing that their model had a correlation between these two things of 0.62, which if we remind ourselves what was going on here, this was widely considered to be kind of outrageous. But what's the paradox then? Well, the paradox is that in this figure, everything has been normalized. So all the time series are normalized to have standard deviation 1 here. But if you don't do that normalization, it looks like this. So here, the gray dots are the actual individual ensemble members. So each gray dot is one realization, one prediction of the winter NAO of that year. And the red line is again the ensemble mean, but it hasn't been standardized to have standard deviation 1. And what you can just see by eye is that the ensemble members are almost evenly distributed above and below 0. So the ensemble members can't even decide should it have been a positive NAO or a negative NAO, really. But somehow there's like just enough ensemble members are saying the right thing that when you take a big ensemble mean, you extract a good forecast. So concretely, that's telling you that there's very low signal-to-noise ratios. Yes?
You're not running a 35-year simulation.
No. So each year is a completely individual forecast. So it's a forecast from initialized November 1st, 1980. You run it for 4 months, and you get a winter. And then you initialize it again the next year.
Okay, I just wanted to be sure.
Definitely no predictability for 30 years ahead in time or anything like that. No. The time series makes it look like it's a continuous, right? But no, it's individual. Thanks. The signal-to-noise ratios are very low, and the practical consequence of that is that you need a big ensemble in order to get any kind of skill at all. And possibly you need even hundreds of ensemble members to really kind of get the skill you'd like. Another way of thinking about this paradox, so by various ways it's been talked about in the literature, but for me the easiest way to understand what this paradox, how to describe this paradox is that the actual skill in a model is a lot higher than the so-called potential predictability. So by actual model skill, I just mean you take the ensemble mean and correlate it with observations. So it's like this ACC. And then the potential predictability is you correlate your ensemble mean with randomly chosen ensemble members and see how good. So potential predictability is how good is a model at predicting itself versus the actual model skill. And somehow, as the name suggests, right, that the name potential predictability, or perfect model skill, as it's also sometimes called, sort of suggests that this should be an upper bound on the scale. But it turns out that that's just dead wrong. And actually, so I think, if you're looking at maybe short-range forecasts in the tropics, that was a very good heuristic, but it turns out in the mid-latitude, when you get to seasonal timescales, it's just dead wrong, and the actual skill is often a lot higher than the so-called perfect model skill. And that's why it's been referred to as a kind of paradox. Essentially, it's a sort of paradox because of the choice of the word name. Potential predictability was sort of unfortunate in a way. But the practical way of thinking about this perhaps is essentially that models seem to drastically underestimate how predictable the circulation is, the mid-latitude circulation is. It'd be great to understand where this paradox is coming from for two sort of clear reasons. The first is that, well, maybe if we could resolve this paradox, we would be able to get higher skill, or we wouldn't have to run hundreds of ensemble members. We could just run 10 or 20, and we'd get the same level of skill. But also, it's this tantalizing question then that, this paradox isn't just on seasonal timescales. I'm going to focus on seasonal, but it's also been seen now in decadal timescale forecast. And again, you have this issue that the real world seems to be more predictable than models think it is. And it just begs the question, right, is climate change in the North Atlantic sector also much more predictable than models think there is? I think it is. Famously, the winter jet stream, the fate of the winter jet stream in the Euro-Atlantic is highly uncertain in model projections. It's one of the places where models can't agree at all on whether the jet is going to move up, down, left, right, or center, right? And maybe there's a relationship here. Maybe it's really very well constrained and the models are just doing something funny. Okay, so I'm going to talk you through I'm now going to talk you through my kind of idea of this and me and Tim's ideas around this. But you can find all the details in a paper I wrote about this. And I'm not going to talk about much technical details. Okay, so why might this paradox be occurring? Essentially, the first paper that came out about this, sort of analyzing this concretely, was this paper, Siegert et al. They used a simple linear regression style model, and their conclusion was kind of a very sort of intuitive one, which is that models respond too weakly to forcing. So there's some predictable signal in the real world, and models are just capturing a fraction of it somehow. So too weak response to forcing. And that's been interpreted to mean perhaps the problem is something about the teleconnections in the model. Maybe there are all these teleconnections that are providing skill, and the models aren't kind of doing these teleconnections properly. And there have been several explicit examples of teleconnections that might be to blame: tropical rainfall, the QBO, Manjulan oscillation, Arctic sea ice. So pretty much the whole range, pretty much every teleconnection that you can imagine has been suggested as being a possible culprit for this paradox. But the other hypothesis, which is what I'll focus on, essentially was put forward by me and Tim in a paper we published in 2019, where we thought about this using so-called regimes. So there have been many studies suggesting that this circulation, the jet stream circulation, and the NAO is somehow influenced by the existence of regimes. And it's natural to ask if that's having an effect on predictability. So if you're not familiar with regimes, the canonical example of a regime system is the Lorentz 63 butterfly, where you imagine that it's somehow, you think about it as having two regimes corresponding to the left and right wing of a butterfly, and the system oscillates between hanging out in the left wing and then chaotically moving to the right wing. And so you can think about kind of a predictability and dynamics of Lorentz 63 as, you know, whether the system is in the left or the right wing of a butterfly. So I'm going to come back to how one can think about the Euro-Atlantic as a, you know, explicitly as regimes. But there have been several studies attempting to do that, and it was kind of natural to ask if that was having something to do with this. And what we propose is essentially, in that paper, is that if the NAO skill is driven by regime dynamics, and I'll explain what I mean by that later, and the models struggle with the persistence of these regimes, then you kind of the signal-to-noise paradox behavior just kind of plops out very naturally, which suggested immediately that maybe the problem is that the regime structure in models is bad. And kind of conceptually, one way to think about what that might mean is that if you think about, another way of thinking about a regime is like a potential well, and perhaps, you know, the real potential wells are quite deep, so there's a high persistence, you know, the system gets stuck in there for longer periods of time, but the model's potential wells are shallow, the system just comes out of there, tends to come out of there too quickly, and this is a sort of fairly generic problem in many models. Now, just for completeness, I should mention that there's yet another quite similar hypothesis was put forward later by, in a paper by Zhang and Kurtman, where they did something similar, but using just an AR1 model. And the conclusion was similar, that they argued that the issue might be to do with persistence. And I should be clear now that, you know, this signal, I'm focusing on the North Atlantic oscillation, but this paradox has been found in other contexts, other parts of the mid-latitude circulation as well. And not all of those places have regime dynamics driving them. So, you know, what I'm going to present is not kind of a universal solution to all instances of this paradox, but it's very kind of focused on regime systems like the Euro-Atlantic. Okay, and the goal of this this talk is to kind of try to sketch out for you a test I did of this hypothesis that me and Tim put forward using actual forecast data. So in my paper with Tim, we hypothesized maybe this is what's going on, and then I went on and tested it with using actual forecast data from the ECMWF forecast model. And you know, it's a standard 51-member hindcast covering 1980 to 2010. And because of how this particular hindcast was initialized, I'm using error 20C as reanalysis, but it doesn't really matter what reanalysis you use. And this is, I should say, these are from experiments carried out by Antje Weisheimer at ECMWF.
Christian, I have a question for you.
Yes.
If you go back to that potential well figure,
Yes.
could you say why do you think it's that reality has the deeper well than the models? I mean, couldn't it be vice versa?
Yeah, there's no obvious reason why it should be one way versus the other. I'll come back to mechanisms at the end. Okay. I can tell you that the sort of slogan or the key phrase perhaps to keep in mind is transient eddy feedbacks, which are kind of represented differently in models.
Thanks.
But I'll come back to that in a minute. So, right, okay, so I've talked about the Euro-Atlantic as a regime system. How am I going to do that concretely? I'm going to do it using these so-called jet latitudes. So if you're not familiar with the jet latitude index, this was cooked up by Tim Wollings and others. And what they essentially do is they try to track the jet as it moves day to day. So what you just do is, on any given day, you look at where the maximum zonal winds are in the kind of North Atlantic region, and you say that, you know, where the maximum is, that's where the jet is. We're just going to say that's where the jet is. And then you can say where the latitude is, where the jet was found on that day. And by doing that for every day, you can kind of track the latitude of the jet as it moves up and down through each winter. And if you make a PDF of this this jet latitude index this is daily jet latitude index, you get something which is very strikingly and clearly multimodal. It has these three clearly defined peaks. Here in the black, it's using reanalysis, and the red is using the ECMWF data. And nowadays, like if you take a random CMIP6 model, it stands a pretty good chance at also showing this trimodality. So this is a pretty robust feature of sufficiently high resolution models, let's say. And that's how I'm going to think about, or that's sort of the base way of thinking about the jet as a regime system. So somehow there are three regimes here. There's the kind of southern jet, a central jet, and a northern jet. And the jet is kind of moving between these peaks. This is a very neat way of understanding the NAO. The reason for that is because it allows you to kind of decompose the NAO into orthogonal components. So this is a schematic I made for a paper that was just published with Josh Dorrington and someone else. Essentially, the way it works is that the NAO is to pretty good approximation captured by variability in the latitude of the jet and the speed of the jet. So if you have those two things, then you pretty much know what the NAO is doing. Now the jet speed is somehow the longitudinal variability of the jet. And if you plot a PDF of that, it's just a Gaussian. It's kind of boring. It's also unpredictable, so models can't predict the winter jet speed. And there's also loads of decadal variability, in how fast the jet is any given decade. On the other hand, the latitudinal variability, as I've just shown you, has this nice trimodal structure. So it's kind of regime, it's, not Gaussian, highly non-Gaussian, and it is predictable. So it turns out that if you try to ascribe the NAO scale to the jet speed or the jet latitude, then there's nothing in the jet speed and everything is coming from the jet latitude. So what the models are predicting is essentially, is the jet going to be, up or down, or north or south each year. And nicely, this trimodal structure is extremely stable. If you go back, if you pick a random time period across the 20th century, you get the same PDF. Now, excuse me. So it took me a while to kind of, to kind of really turn this, to really relate the daily jet dynamics to the NAO. We need to understand, of course, how, more concretely, how these two indices, the jet speed and the jet latitude, impact the NAO. And I was very surprised personally to make this plot. So what it's showing, right, is on the top panel, it's using reanalysis, and the bottom panels is using model data. And on the left, it's daily jet latitude versus daily NAO index. And on the right, it's daily jet speed versus daily NAO. And somehow this isn't surprising, right? That the jet speed, where everything is Gaussian, there's no, everything is linear, so the relationships are linear. But in the jet latitude, where you had this highly non-Gaussian structure, the relationships are non-linear. Like you can just plot it, and you see that you get some kind of interesting, more complicated structure emerging. And this, probably this is. I had never seen this before I plotted it myself, and probably the reason for that is that if you take seasonal means now, so DJF means of the same, it's the same plot, but I've taken a winter mean of everything, then all that interesting structure has just vanished, right? Everything has now collapsed into some kind of linear relationships. So somehow the moral is that there's lots of interesting structure on daily timescales, which is just lost, smeared away when you take some kind of seasonal average. And the hypothesis, essentially, the hypothesis that me and Tim put forward is that this multimodality is and this non-linearity and all this extra structure is actually important when it comes to understanding predictability. But okay, then you need to, right. So that was the hypothesis. How does that work in practice? Well, we have a clue already from a paper by Quoty, Molteni, and Palmer, building on work from Tim, where they used the Lorentz 63 system and observed that if you stick some forcing into the Lorentz 63 butterfly, then what happens is not that it's not as if the wings of the butterfly move or anything like that. All that changes is the amount of time spent in the left wing versus the right wing. So if you put a forcing sort of in the direction of the right wing, then the system spends more time in the right wing than the left wing. But the actual attractor looks the same, as long as you sample it long enough, of course. So in other words, when you put a forcing in a regime system, what changes is the frequency of time spent in the regimes. And there have been a few papers showing that this happens also in the Euro-Atlantic, where, for example, if you have a sudden stratospheric warming, then that changes how much time is spent in different regimes. And also papers looking at the Madden-Julian oscillation and ENSO, how they modulate regime occurrence as well. So with that in mind, here's what we're going to do. We're sort of starting, this is our kind of starting point. Now, I've talked a lot about the trimodality, but for reasons that I'll explain in a bit, it ends up being useful to truncate into a bimodal system in this following way, and think about the jet as oscillating between a south and a north regime. And then if you just stick some arrows on here, then suddenly you've got yourself a Markov chain, yeah? And that's how we're going to think about this system, what we call the Markov Model approach. So we're thinking about the NAO as just being completely determined by the jet bouncing between a southern regime and a northern regime. So every day it might be in one or the other, and it has a certain probability of staying in that regime and a certain probability of transitioning to the other regime, and it just moves around like that. And you can do some simple maths here and show that the long-term mean NAO in this system is just a function of these probabilities and these arrows. So these arrows are just saying, what's the kind of what's the average NAO like on a southern jet day, and what's the average NAO like on a northern jet day? And if you have that information and you have these probabilities, you completely reconstruct your NAO. And the NAO, just to spell that out, the winter NAO is therefore equivalent to just a 90-day random walk in this system, right? A winter is 90 days, so you just take a 90-day random walk here, and you get an NAO. And the predictability is completely coming in the system from these persistence probabilities P and Q. So the idea is that P and Q are different from year to year. So they're not the same every year, they vary from year to year, and that gives you an anomaly in the NAO, and that allows for some predictability to arise. Now, if you do this, and you try to look at things like persistence, I'm not going to spell out, I don't want to spell out what exactly this is showing, but essentially it's the fact that essentially you can easily show that the persistence is somehow biased in the low direction in models. Now, this is kind of I find a more interesting plot. So what you can show is that, the IFS does have skill at predicting these persistence probabilities P and Q. So as I was just telling you, right, all the skill is coming from somehow these probabilities changing from year to year, and you can show that the ECMWF model, the IFS, can predict these variations. And the way it predicts it is like in this decomposition, which I've shown you. So what is this 3D plot? I've just taken the jet latitude and I've extended it out by, essentially it's out in the jet speed in this PC0 is essentially the jet speed. So I've just kind of extended the jet latitude out in an extra dimension. So this is what the IFS somehow sees, and somehow What it can't see is it can't see the southern regime. And if you look at this, as soon as I made this plot, that became kind of intuitive. Why? Because somehow the northern regime is really pronounced and separate, while the southern regime is more like a quite subtle shoulder in the distribution, actually. And the IFS can't really see that. But it can see this division, and that gives you some skill. How you show that it gives you skill, I'm not going to tell you what these equations are. The point is just, once you've got this idea of the Markov model, you can fit some statistical model, and you can fit the model to the actual forecast data, and you get some numbers. And in particular, I'll just point out that this beta parameter, which appears in these equations, is less than 1, and that's exactly corresponding to a kind of damping of persistence in the IFS. Now, what about the paradox? This is if you simulate what the actual skill and the potential predictability is as a function of ensemble size here, then you get this plot. So the solid lines are what's predicted by this Markov model, and the stipple lines are what you would estimate using actual forecast data, and then there's some error bars. And the point is just that pretty much immediately in this model, in this setup, you get this feature that the actual skill is much higher than the potential predictability. So the moral of the story there is just that if you have a regime system, then this paradox is essentially automatic. Right. And just to show you the kind of, I was showing you this plot using the Markov model. This is just showing you that you get exactly the same kind of behavior here. If you do a random draw using this regime model, you get these kind of plots where the individual ensemble members are all over the place. But if you take the average and normalize it, you get something which looks quite nice. Okay, so I glossed over all the technical details, but essentially that was the moral. You can cook up this regime, statistical regime model, and explain the paradox and link it to persistence in some way. Now you might be asking, that's kind of neat, but have we really gained anything, right? Isn't it easier to work with linear regression or AR1 approaches? What have we actually gained here, practically speaking? Is this just some kind of neat statistics or something? And I'm going to talk you through what I see as real gains to this approach. Firstly, this is a more philosophical, I guess, gain, but it's just that it respects the structure that we actually see, right? So we see that the jet is trimodal or multimodal on daily timescales. Probably it's important. We know there's this thing about flow-dependent predictability. Probably that's important. And when you kind of truncate the whole system to just a single NAO index or something like that, something similar, then you just chucking all that out. More practically speaking, thinking about it this way immediately points to what might be relevant processes influencing this stuff. So we've linked this paradox to persistence in the jet. And it's natural to then ask, well, how do we get persistent anomalies in the jet? And of course, there's an incredible wealth of literature, starting with people like Brian Hoskins and Glenn Schutz and many others after that who have looked at this and pointed out the importance of transient eddies for reinforcing jet anomalies and keeping the jet persistence. In more recent years, there's been an emphasis on more kind of moist processes. For example, warm conveyor belts, how they come in and add energy to the jet. So this points to potential processes that are important, and there have been some hints at what might be going wrong here. This is a nice paper by Adam Scaife in 2019, where they looked at essentially what this is showing is somehow it's some attempt at measuring the strength of the eddy feedback, let's say, at different resolutions. So all the way on the right, it's a low resolution. I mean, the resolution goes up a little bit, goes up a bit again, and then you've got this, the sort of most high resolution one is this it's about a 10 kilometer simulation, and then you've got reanalysis all the way on the left. And I mean, the error bars are massive on this highest resolution one because there wasn't much data, but perhaps there's a hint here that, you know, there's not much that's going to change or improve here until we are really resolving fine scales here, right? These transient eddy feedbacks are somehow very complicated interactions between small and large scales, and maybe they need very high resolution in order to really be represented. And furthermore, you know, it's sort of clear that low resolution models do have lots of issues with representing this very fine scale behavior, and that might be why, for example, they have weak persistence in the first place. This third gain is the importance of mean state dependence. So coming back to this picture from Tim's paper about the Lorentz butterfly, what this somehow tells you is that, you know, if you want to get the response to forcing correct, it's not just enough to know where the arrow is pointing. So it's not just enough to know where the teleconnections are pointing. You actually have to have the butterfly wings in the correct place as well, so that the forcing is coming in correctly. And the same will be true in the Euro-Atlantic. So, you know, we had this interesting feature that, you know, the model can't really distinguish between the southern jet in red here and the other two regimes. And so on the left here, it's reanalysis again. On the right, it's the model, the Eastern WF model data. And you can see it even more clearly there that this southern jet is really kind of, you know, it doesn't seem like a pronounced feature in the model at all, right? It's really just smeared out quite dramatically. And of course, that leads you immediately to ask, well, why does there even exist a southern shoulder in the distribution at all? And the fact is that nobody has any idea why the jet latitude appears to be trimodal in the first place. But you know, that would be clearly an interesting question to answer and understand. And finally, and perhaps most interestingly or excitingly, this framework allows you to really understand non-linearities. The equations here, you don't really need to worry about them, but the point is that through some simple Markov chain maths, the NAO, the final NAO index you get, is a non-linear function of these persistence probabilities, P south and P north here. And what that means is that this gives you a very concrete way of understanding non-linearities. So it's just a general feature that in papers that look at teleconnections to the NAO, you seem to see non-linearities, strong mean state dependencies, and all this kind of complexity. And this is very easily understandable in a regime context by thinking about how teleconnections force regimes in an asymmetric fashion. And just to give you an immediate example of what I mean by that, here's a figure that Bernard Jimenez Esteve made for me, where we looked at the quasi-stationary waves. So you do like composites of quasi-stationary waves in seasons where you have a northern jet regime and versus where you have a southern jet regime. And what you can see is that the picture in the southern state is not just the opposite of what happens in the northern. It's not like you just flip the colors. You have a very clear preference for one kind of forcing in one regime and not in the other. So forcing seems to project quite asymmetrically on these regimes. And that would show itself as nonlinear behavior in the NAO. Another example is sea ice. There's been loads of debate about if there is or isn't a teleconnection from Arctic sea ice to the mid-latitudes. Here's just the plot. It's showing, this is showing essentially grid point correlations between sea ice concentration and these persistence probabilities. And the point is just that there is a signal, there are correlations for the northern regime and that aren't for the southern regime. So again, there's some indication that there's some asymmetry here. Forcing is preferentially modulating one regime and not the other. And finally, for ENSO, it really looks like ENSO is mostly acting to modulate this southern jet behavior. So this is like, so what this is showing is grid point correlations between November SSTs and some measure of eddy forcing in the southern regime. And what you can see is that there's a absolutely enormous ENSO-like signal here, and it just doesn't really appear in the same way when you look at the other regimes. So the kind of moral of that is, and this is nearly at the end here now, the moral of all that is essentially that this framework for looking at the jet variability, by decomposing it in this way, it allows you to kind of resolve, as it were, the tug of war. When I say resolve, I don't mean kind of solve it. I mean in the more mathematical sense of splitting it into actual components. The tug of war of the jet, of course, is just this idea that there are loads of different things, teleconnections and forcings, et cetera, that are coming in and trying to move the jet one way or another. And there's this big tug of war trying to determine where it's going to go. It's very hard to do that in just using the NAO index or something similar like that, or a linear, purely linear framework because of all these non-linearities in the system. But if you decompose it in this regime way, then you can much more sort of, it's a lot easier to think about, because you can just think about, well, one teleconnection is coming in and affecting this regime, and another teleconnection is coming in and affecting that regime, and then you get some combined impact at the end. And that takes me to my final slide. So just to summarize all that, essentially, this kind of picture of regime dynamics of the jet can kind of explain this curious paradox in the IFS. I say IFS there a bit, I mean, this could apply to any forecasting model. And then importantly, the regime dynamics are not just set by teleconnections, but also these local processes, eddy feedbacks, and so on. And biases in both of these things are probably important for where the paradox is coming from. This has the neat benefit of allowing you to understand non-linearities easily. And for me also, it's just nice to have a way of thinking about it which kind of respects this complex structure that we seem to see. So thanks very much.
Yeah, I was just wondering about the metric that you showed of the persistence bias in IFS. Is that true just generally of all models?
So I've only plotted that for the Med-Office model and the IFS, and a couple of climate models. But yeah, generally for the models I've looked at, certainly for the forecasting models I've looked at, they both show this general underestimation.
Okay, and that's really the key for the regimes to explain this, is that?
Yeah, well, that's a slightly subtle point which I kind of glossed over a bit here. What is key to get the paradox in this system is A, your forecasting model has skill at predicting these persistence probabilities, but B, it messes them up as well. And the way in which it can mess them up might be a bit complicated. So one way it can mess it up is just uniformly damp the persistence anomalies, but it could also be doing slightly more complicated things. It's not true, as far as I can tell, sufficient that it just kind of uniformly damps the persistence probabilities, and that's it. So probably that, there is still a contribution here from the remote teleconnections, as far as I can tell. So it's not just that the local feedbacks are too weak, for example. It's probably also that the signal coming in is not quite correct. And intuitively, that makes sense, right? It's never as simple as just one or the other. It's a combination of both, yeah.
Okay, yeah.
Maybe naive question. This is winter time. Is there anything going on interestingly for summer?
Good
Maybe
question.
some blockings or something like that?
So people have tried to look at regimes in other seasons than just winter, but generally you don't see the structure is not as clearly multimodal in other seasons, including summer. So if you do the jet latitude index, for example, in the summertime, you just don't get any multimodality. And that might just be because the jet is too weak the jet is much weaker in the summer than it is in the winter. And so maybe, if you had an artificially strong summer jet, you would still see it. But essentially, the answer is you don't really get this regime dynamics in other seasons.
So you argued, I think, that you can fit a simple Markov model to the data. And then I think you were saying that that Markov model shows the same paradox as real IFS forecasts show. So if you make any error in the Markov model, do you get this paradox? Or is there sort of a specific class of things that you do wrong? I mean, there's only two numbers, like P and Q.
Yeah.
What class of errors in P and Q yield this paradox?
Yeah, good question. Again, it sort of comes back to what Isla was asking about too. So I tried a few different things playing around with this model, and essentially, as far as I could tell, most ways in which you mess up these probabilities will give you the paradox. It's not true that, of course, you can't, so the challenge is to kind of mess it up or get the paradox that matches what you see in the data. You can't just do anything and get the same numbers as in the forecast data, but basically any which way you mess up the probabilities will give you this feature that the actual scale is a lot higher than the potential predictability, as far as I can tell.
Thanks very much. I have a comment and then a question. So the comment, and we talked about this a little bit, is if you have a AR1 model, so much easier than one you looked at, an autoregressive process first order, and you perturb the autoregressive parameter with a white noise forcing, it's analytically really simple, you actually get an increase in persistent. You get a longer decorrelation time. And so that would be really interesting to look at, and it would give this link with a high resolution sort of idea that you might need a high resolution to get the persistence right. So this is my comment. And my question is, you said you would tell us why you went to a 2 regime rather than a 3 regime
It was this
model, and I'm interested in that.
It's this, I guess the true answer is essentially that I checked what the IFS could and couldn't predict, and the answer was it could predict that bimodal system, and it couldn't predict any other combination, trimodal or bimodal, that I looked at. Or the 4 regime, if you're familiar with the 4 regime picture of the Euro-Atlantic, it also can't really do that. And I think, for me, it was this plot which kind of made it intuitively clear why that's the decomposition that works. It was perhaps a bit easier in the other one. Somehow the IFS is truncating this shoulder into the central regime to some extent, and just kind of all the forcing just gets projected onto this one regime, and then that's it. So the caveat there is, there's ongoing work I'm doing to try to see if you can get a better picture anyway using the three regimes. But yeah, I don't have a clearer picture currently than this.
Okay, well, we'll do those last.
All right, I'm going to put forth the hypothesis that the model cannot predict the southern regime because it doesn't really know what's going on in the tropics. It probably has parameterized convection and doesn't really know what's going on there. So is that possible?
So I'm not. I mean, for me, it comes back to this question of why do we even have this southern shoulder, even at all? Because you might think that it's got bad ENSO teleconnections or something, but
I'm meaning more weather, tropical weather, equatorial waves.
Right.
Not like large scale phenomena, but just blow-ups of convection. Sometimes they happen in the ITCZ. Those kind of things.
Yeah, it might be. It might be that that's part of it. Those are the things that aren't being represented properly, and those are crucial to get the forcing onto the southern shoulder. I somehow have this, it doesn't seem like a coincidence to me that the subtropical jet is sitting right above the southern jet. So when you have, so this is the eddy-driven jet we're talking about, right? And when the eddy-driven jet is in the southern state, it tends to be merged with the subtropical jet. And it kind of really suggests to me that, is there some kind of link, some kind of coupling here, which, is just not being done right in the forecasting models? That would be my other guess.
And a quick question, how long of a time period would be enough from an NWP model to get the trimodal structure? Do you need years? Would a season be enough to kind of see
probably
it?
not just a random season, because you can have winters where the jet more or less stays entirely in one state,
Right.
or just in two states for the entire season. So that would give you the wrong impression. But I don't know, 5 to 10 years, and you'd probably have a decent, using daily data, you'd probably have a pretty good approximation.
All right. Thanks.
Okay, there are no further questions from the room. We'll go to the Slido questions. We have a question here from Rosimar Rios Barrios. Have you thought about looking into how jet expansion or retraction, for example, the work of Andrew Winters and collaborators, may be affecting the trimodal distribution of jet latitude?
No, I haven't, and I'm not familiar with that work, I have to admit. So it's too bad you're not here in person. You could tell me what it is. Jet expansion? No, the answer is no. But you can leave a comment maybe and update me.
Okay, the answer was no.
Yes.
So one more question for you. This hypothesis about the eddies not being resolved and therefore not being able to feed the jet sufficiently, has this been tested, or has it been tested in sort of a simplified channel models with high resolution?
To some extent, yeah. There's a kind of, I guess in very simplified settings, it has been tested, and you generally have two-week transient eddy feedback, which gets stronger as you increase the resolution. The sort of complexity or the difficulty is that, of course, low-resolution models don't have any kind of multimodality or anything like that also. So it's,
For just that one particular component of this argument.
Yeah.
Is there something else that would be needed too?
I think, okay, I mean, I don't want to, I feel like this is the sort of question I should be able to answer immediately, and I can't on the spot now. I think the answer is yes, but only in simplified contexts, yeah.
Okay, well, thanks again, Kristian. And a round of applause. And next week,